Let's do another example of solving a minimum spanning tree. So step one, select the cheapest edge and highlight it. There we go. In this graph, we've got 4 as the cheapest edge. And notice here, the numbers are, again, this graph is made a little differently. It looks a little weird, but basically, occasionally you'll see people put the numbers kind of overlapping the lines. Again, this is not really proper graph theory, but a lot of times you can, read between the lines, both figuratively and literally, and that was a horrible joke. And, you kind of get what the graph is getting at, but, with proper graph theory, we don't really do this where we have the line split with the number in between, but I think we can figure out what it means. And basically, step 2, select the next cheapest edge. Step 3, select the next cheapest edge. And I think this is probably the actually easiest algorithm of any of the ones we've done so far, because you're just picking the cheapest line and highlighting it with the one condition that we cannot create a circuit. So notice the next cheapest is 12. That one I don't want, because that would form a circuit between A, C, and D. Then pick the next cheapest edge, which is 18, I believe, 19, and just keep doing it until they're all connected. And when I personally solve these, I don't actually use n-1. I just kind of eyeball it and say, I can kind of see, well, when are they actually all connected, and make sure that I'm not making circuits. So next would be 21, I believe. And really, each edge that I add should be bringing something new into the network. So notice that that edge brings G in. And so that was necessary. Next cheapest is 22. That one will bring B into the network, which it currently was not. Next up is 23. That will connect EF to GIH. And again, that was also necessary. But next up, 24 is not necessary. Again, because that would form a circuit. Really, all of those are already linked together. I don't need to build an extra connection. Same exact thing with 25. That would form a circuit. And the other question is, how do I know when to stop? But basically, currently, this left part of the network is disconnected from the right part. So eventually, they're going to be connected. But if I keep following Kruskal's algorithm, I'm going to keep selecting the cheapest edge until I run into n-1 edges. The next cheapest is now 30, and that would finish my spanning tree. And now everything is done. And again, there's no circuits there. But basically, there's a lot of different ways to do it. I'm trying to give you a few different tricks and processes that I use. But anyways, we know that we're done once all the vertices have power or whatever the problem is, once they're all connected. And assuming we have not used, assuming we've done it in a minimal way, actually found a minimum spanning tree. And then the net weight here would be, I'll just pull up my calculator to do this. Be 22 plus 9 plus 4 plus 30 plus, it doesn't matter which order you add them up in. And it looks like the net weight here would be 146. So again, imagining that it was the same type of problem. And like we could apply this logic to lots of different types of network situations. So this could be the cost of constructing power lines, railroads, just regular roads, water lines, tubes, internet connections, so on. In our society, there are so many different types of networks, planned networks, where we're trying to connect things together. It's an integral part of modern society, which the relevance of this math has only gotten more and more important over the years as our society has become more integrated and complex. And anyways, what's actually nice is there's quite a simple and straightforward method of solving these problems, which, as you can see from a lot of the other chapters we study, is not always the case. So it's kind of nice. I kind of like that there's such a straightforward way to solve these. In the next video, we'll find maximum spanning trees for the same problems.